Hi there, this is Matt Heffernan. Welcome back to my channel. This is the fourth episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system starting at the very lowest level. If you haven't seen the first episode, I strongly encourage you to go back to my channel and don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. So far in this series, we have learned the basics of assembly language and went over all of the different addressing modes supported by the Z80. We looked extensively into how to move data around, and in each episode doing some simple loops while using conditional instructions. In this episode, we will go in depth into how the conditional mnemonics relate to the status register bits, and how each instruction makes use of them to provide flow control to programs on the spectrum. As we saw in the episode on addressing modes, all of the conditional instructions for the Z80 are based on status flags, which are reflected in the F register. Each bit in the F register is set in different situations, and half of them can be used by conditional instructions, starting with the most significant bit, named S for signed. This bit indicates the result of the last operation that affected the sign of the value in the accumulator, with S being set to 1 when the value is negative. So effectively, it is the same as the most significant bit in A after the last instruction that could have affected this bit. Not all instructions affect bits in the F register. Even those that change the value in A leave the flags alone, such as the load instruction. Most of the time, loading a value into A does not affect this bit, but a mathematical operation will. It can be a bit confusing, but as we go through this series, we will always indicate when status bits can be affected. Moving on, the next bit is Z for 0, which is set when an operation has a result of 0. Despite the official description of this referring to the value in A, it also applies to any increment or decrement instruction on any 8-bit register. So the Z bit is the one that is used most for loops, where a register can be used as a loop index, and then incrementing it up to a specific value, or decrementing it down to 0, which is usually quicker, and what we have seen so far in all of our example loops. Bit 5 of the F register is not a status, but rather a record of how flags have changed. This is really a side effect of the Z80 design, but you will see that when an instruction with an 8-bit opcode changes any of the flags, bit 5 of that opcode will be stored in bit 5 of F. The same thing goes with bit 3, which is another side effect. So if for some reason you need to determine recent execution history, you could examine these two bits to help determine what instruction led to a certain part of the code. Bit 4 is another insight into how the Z80 works internally, with H for half carry. Unlike most 8-bit processors, the Z80 arithmetic logic unit is actually only 4 bits wide, so doing things like shifting or addition actually requires 2 passes through the ALU to handle each nibble. The H flag is set when the operation on the lower nibble required a carry into the upper nibble. You need to examine the F register to see this, as there is no condition mnemonic for it. Skipping ahead to bit 2 is the dual-named PV bit, which does double duty as a parity bit and an overflow flag, depending on which instruction was used. There are other uses for it too, but most of the time it is used for overflow, which means that the resulting sign of an operation is not what would be expected. Bit 1 is the N bit, which is set when a subtract instruction has been executed since the most recent addition instruction. If that matters to your program, you can examine the F register to check it out. Finally, the lowest bit is C for carry, which is the full 8-bit carry flag, as opposed to H. This bit figures heavily into math operations with 16-bit or larger values, as well as many other use cases. There's a lot to unpack here, but in this video, we aren't going into depth for each bit. Instead, we are focusing on how these 4 are used with conditional instructions, using the conditional mnemonics we have already seen. But for review, there are 8 different mnemonics used for conditional operands, and they are always used as the first operand in the instruction, and often the only one. C means the carry flag is set, so the instruction will only take effect if the C bit is 1. If we want to check the opposite state, we use the NC mnemonic for not carry, as C equals 0. Similarly, Z and NZ are used for the 0 bit, for 0 or non-zero, which can also mean equal or not equal for comparisons. For the sign bit, we use M for minus, meaning S is 1, or P for plus when checking for S to be 0. For the PV flag, you use PE for it being set, or PO for it being clear. While we generally care about the PV flag when it's used to indicate overflow, The mnemonics stand for parity even and parity odd, as most of the time that's what the current state of PV is indicating. We've seen a lot of the jump instruction already, including using it with a conditional operand. But to be completely clear, the JP instruction takes an absolute 16-bit address and loads it into the program counter, or PC register. When it only has a single operand, it's an unconditional jump, meaning that address will always be loaded into the PC. It can use the extended immediate mode to have the address right in the code, or it can use register indirect mode to use the address currently stored in HL or one of the index registers. If JP has two operands, the first will be a condition mnemonic, and all 8 conditions are supported. However, the target in the second operand must be an immediate address, so you can't do a conditional jump to an address in a register in a single instruction. We've seen simple loops already as well, but now we should have a better idea of how they work. The easiest way to make a loop is to use a loop index preloaded with the number of iterations to perform, and then decrement at each iteration, and keep going until the Z bit is set, meaning the value in the register has gone down to 0. Here we see how we can use the Z bit to multiply the value in A by 32, which we can accomplish by shifting it 5 bits to the left. So we could do 5 straight SLA A instructions, or we could do a loop that does SLA once per iteration 5 times. So we preload B with 5, then have a label for the beginning of the loop iteration. After the label, we do a single SLA A, which will shift the value in the accumulator 1 bit to the left, filling in the lowest bit with 0. Then we decrement B and do a conditional jump to the top of the loop. If the decrement resulted in a non-zero value in B, then the Z bit won't be set, and the jump will happen because we specified the NZ, or non-zero state, which is true when the Z bit is clear. Once B is decremented down to 0, the Z bit will finally be set, and then this jump instruction will effectively be skipped, and we fall out of the loop and continue on to the next instruction after the jump. One of the main ways to affect the status flags purposefully is with the compare instruction, which has the mnemonic of CP, and then an operand for a value to compare to the accumulator. You can use most 8-bit registers, including A itself, which is an easy way to force the Z bit to be set and the C bit to be clear in one instruction. The only registers you can't compare directly are I and R, so that will require shifting register values around a bit. But luckily, there are a few reasons to do that. You can also do an immediate compare with an 8-bit value, which is how you would use a loop index that increments up rather than down. You can also compare A with a value in memory, using either the register indirect mode with the address in HL, or with indexed mode, using an offset from either index register. The most common use of compare is to see if a value is simply equal to the value in A, which we can see with the Z bit, which is set when the values are equal, and cleared otherwise. If you are assuming both values are unsigned, you can use the C bit to determine relative value. If the value in A is less than the value from the operand, the C bit will be set. But if the value in A is greater than or equal to that value, C will be cleared. Of course, we've seen even more of JR so far in this series than JP, as it's a relative jump and can be executed more quickly thanks to the target being an 8-bit offset from the next instruction address, rather than an absolute 16-bit address. One less byte to fetch for the instruction gives us this performance boost, as well as making the program take up less memory. If you know that the target address is going to be within that 8-bit offset, it is best practice to use JR instead of JP. In fact, with any label, just use JR at first, even if there's a remote chance, and let the assembler let you know if the target label is too far away. And then you can just change the JR to a JP, and it should assemble just fine. You can do an unconditional JR to always apply that offset to the program counter, or you can do a conditional JR. However, you can't use any condition with a JR like you can with JP. Instead, you are limited to just using the C and Z bits. So if you want to do a jump based on overflow or sign states, you need to use an absolute JP instruction. Luckily, jumping on those conditions are a lot less common, so you don't have to worry too much about this restriction causing your code to be bloated. In our examples so far, we've only seen return instructions used to end our programs, but more often they are used to return from subroutines within a program. In either case, you can do an unconditional return by just having the RET mnemonic with no operand, and the next execution address will be popped off the stack and loaded into the program counter. However, you can also use any condition mnemonic as an operand, and only return if that condition is true. This can save you the trouble of having to have multiple conditional jumps to a single return instruction in the code. You can just do a conditional return at any point in your subroutine, as long as all possible execution paths end in a return, so it's good practice to always do an unconditional return at the end. The most common flow control construct in high-level languages is the if statement, which is very simple to implement in Z80 assembly using compare instructions and conditional jumps and returns. At the left, we see the body of a simple C function that normalizes a variable called foo towards a value of 42, incrementing or decrementing to get closer to it if it's not already that value. So in C, we can do this with an if statement that will be entered if foo is not already 42. Then an embedded if-else statement that will do an increment if foo is less than 42, or a decrement otherwise. At the end, we just return from the function. Of course, in assembly, we don't have the same concept of code block hierarchies, or even an if statement. So first, we need to check the value of foo, which we can assume is an existing label for an 8-bit value in memory. We load the value into A, and then do an immediate compare with 42. If the value is already 42, the Z-bit will be set, so a ret Z instruction will let us return immediately. If Z is clear, we know that the value is not 42, so we continue on to a relative jump to the too high label if the C bit is clear. In this case, we know the C bit will be clear if the value is larger than 42, and thus too high. If we didn't take that jump, we know that C was set, meaning the value is too low, so we increment A and then jump ahead to the done label. Then we have the too high label, where we decrement A, and then continue on to done, where we write the adjusted value in A back to memory. Now we do an unconditional return, as our subroutine is finally done. While the assembly code may be a bit more involved than the C code, it would generate only 16 bytes of machine code and run very quickly. The call instruction is what we use to call a subroutine in the first place. It is responsible for pushing the next instruction address to the stack, so that the next executed return instruction will pop it into the program counter and have the program pick up where it left off. In the meantime, the PC gets loaded with the address specified in the operand, and the subroutine starts executing at that point. If the address, or a label that resolves to an address, is the only operand, then it is an unconditional call, and the subroutine will be executed every time. If you precede the address with a condition mnemonic as the first operand, then the subroutine will only be called if that condition is true. Call supports all 8 conditions, so there's no need to use conditional jumps just to get to an unconditional call. The last instructions that solely affect the status flags are a pair that can simply clear or set the carry flag, called CCF and SCF respectively. These come in handy when you need to use an instruction that is affected by the state of the C bit and need to get it to a known state first. None of the other flags have special instructions like this, but we will see in later episodes there are different ways to control the processor state. There is one more conditional instruction that doesn't use any status flags as inputs or outputs. We've seen it briefly before, but here it is again, DJNZ, or decrement and jump if not 0. Rather than doing separate decrement and conditional jump instructions, a DJNZ will decrement the B register, and if it's not 0, do a jump to the specified address, which must be a relative offset rather than an absolute address. This is a quick and easy way to end a loop, as long as the code inside your loop isn't so big that it requires a jump to an absolute address at the end. On top of that, none of the status flags are affected by DJNZ, not even the Z flag, which would be set once B got down to 0 if you were using a separate decrement instruction. We'll see how all of these conditional instructions work in the example program, which will take a string and print it out 3 ways, using the original characters, forcing all letters to lowercase, and finally forcing all characters to uppercase, all using different approaches that are available on the Z80. Let's go right to the code. We're back in Atom for our text editor, and using sjasm Plus for an assembler, so we start again with the device macro to specify the 48K spectrum, and an org statement to place our code at hex 8000. We do a jump to the start label so that we can have some data in memory before our code really starts. First, we need to define some character codes, including the enter key and codes that define which characters are letters and what their cases are. The letter codes for the spectrum are the same as ASCII, so we expect uppercase letters to start at hex 41 and lowercase letters to start at hex 61. Our one bit of data will be the text message that we'll be printing out, which contains some very good advice. We have a comma after the string literal to append an enter code, so that when the whole string is printed out, it will automatically include the new line character at the end. Then we have a macro to calculate our string length, using the $sign to stand in for the address of the current line, and subtracting the address of the message label to get the total string length, including the enter code. At the start label, our code begins by loading the message address into HL, and initializing B with the message length, as we'll be using it for a loop index. Each loop iteration begins with loading a byte from the address in HL into A, which will be a character code from the message. We then print it out using the Spectrum ROM routine at hex 10. We move on to the next character by incrementing HL, and then doing a DJNZ to decrement the loop index in B, and jump back to the top of the loop if B isn't 0 yet. Once B gets down to 0, every character in the message, including the terminating enter code, has been printed out in its original state, and we fall out of the loop to start printing more characters on the next line. So now we move on to print it out in all lowercase letters, and we start the same way by loading the message address into HL again. For this loop, we won't be using a loop index, but instead we'll keep printing characters until we come to the enter code, assuming that there is at least one printable character in the message before enter. For a reason that we'll see in a few lines, we load the first character into A before the loop starts. Then each iteration starts with comparing the code in the accumulator to the code for an uppercase letter A. If the code is less than that, the carry bit is set, and in that case we jump ahead to the print lower care label. Otherwise, we compare it once more to the code one higher than the code for uppercase Z, or Z for those who insist on such things. If it's less than that, we know this code is an uppercase letter, so we call the to lower subroutine when the C flag is set. If the flag was clear, then it's something other than an uppercase character, so we just continue immediately on to print lower care, which we would have skipped to earlier after the first comparison if C was set in that case. If we did call to lower, we will end up here when that subroutine returns, so no matter what, the program will make it to here. At this point, we know that the accumulator contains a character code for something other than an uppercase character, and we print it out with another RST10. Then we increment HL to get to the next character, and load it into A for the next iteration. But first, we compare it with the enter code, and then jump back to the top of the loop if it's anything else. Once we do have an enter code in A, we fall out of the loop and print that code before moving on. We've got one more version of the message to print out, this time in all uppercase. We're going to make this loop a bit more straightforward, like the first one, initializing again by loading the address of the message into HL, and the length into B. In each iteration, we load a character code into A, and then unconditionally call the toUpper subroutine, which we will see affects only lowercase characters. Then we continue on to print out the possibly converted character, increment the address in HL, and then another DJNZ to keep looping until B gets down to 0. After that, we can simply return from the program. Now we need to define the two subroutines we called earlier. First is toLower, which only got called when an uppercase letter code was in the accumulator. So all it needs to do is add hex 20, which will change it to the corresponding lowercase code. Then we just return, and that subroutine is done. Because of its simplicity, the code calling it needed to be more complex. For toUpper, we wanted to have the calling code be as simple as possible, so all of the conditional logic needs to be built in. We know that A will contain a character code, but we don't know anything else about it, so first we compare it to the code for a lowercase a. If the code is less than that, the carry flag will be set, and that lets us know that it's definitely not a lowercase letter, so we just want to return immediately. By doing a conditional return, we can just return without having to jump anywhere else. But if the C bit was not set, then the code is at least the value of the lowercase a code, so it could be a lowercase letter. We do another compare, this time with the code after lowercase z. If C stays set, then we know it's a lowercase letter, but if it clears, then we don't want to change the code in this case either. So we do another conditional return, but this time only if C is clear. If we haven't returned yet, we know that this is indeed a lowercase letter. So we subtract hex 20 to get the corresponding uppercase letter code, And we can now return unconditionally. And that's finally all of our code. So all we have to do now is generate a snapshot file. So we instantiate the savesna macro and tell it to output a file named cond.sna and have it execute the program from the start label. To build it, of course, we have a build script. We just call sjasm plus with the LST option to generate a machine code listing, and then pass it the name of our assembly file, cond.asm. Now let's go to the terminal and run it. We run build.sh, and then do a directory listing, and see that the cond.sna snapshot file is there. So let's load it into the emulator. We're using Fuse again, so we hit F3 and select cond.sna and let it run. And now we see the 3 lines we were expecting, getting the message across loud and clear. On that note, let's end this lesson here. There's a lot more to come, but for now, please check out the GitHub repo linked in the description, where you can find this code and try running it yourself. And better yet, modify it to do something different. Try out using the different condition mnemonics and see what you can come up with. Next time, we'll get more into how arithmetic and logic work with the Z80, and we'll see how some of the status flags factor into that, and how we can use these conditional instructions to do more complicated math. In the linked GitHub repo, you'll find not only this code, but all of the code examples for each lesson, and all of the slides presented in this series. In the README, you'll also find links to some additional materials that can help explain what's going on, and provide some needed background in case your programming experience is a bit limited. Please subscribe to my channel and click the bell to be notified when the next episode comes out. And please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.